Hello, everybody. Today we just have a short lesson on section 6.3, which is on the central limit theorem. And so here we're talking about using sample means to represent a population mean. And so we're going to utilize these properties that the mean of sample means will be the same as the population mean, and the standard deviation of the sample means will be smaller than the standard deviation of the population. And it'll be equal to the population of the standard deviation divided by the square root of the sample size. And that is represented down here as well. And so when we're taking the standard deviation of the sample, we'll call that, when we're taking the standard deviation of the means, we'll call that sigma sub x bar equals sigma over square root of n. And so what the central limit theorem is saying, which is what this is the only theorem we're going to actually utilize in today's lesson, is that the means of all the samples that you take will be the same as the mean of the population, and the standard deviation will be equal to this quantity that I just showed right here. And so an important note related to the central limit theorem is that in order to utilize the central limit theorem, you either have to have a population that's normally distributed, or if you have a population, I should say a sample. If you have a sample from a population that's normally distributed, then you're good to go. Or if you're not sure if the sample is normally distributed, then make sure that you have a sample size of 30 or greater in order to utilize the central limit theorem. Okay, so let's look at an example of how we can use this central limit theorem. So in example 1, we have an elevator that has a 4,000-pound capacity. The placard says 4,000 pounds or 27 passengers. So we're trying to analyze, is that realistic that 27 passengers is about the same as 4,000 pounds? So if we, let's suppose that we filled the elevator full of adult males. Is there any chance that we're going to have an average small enough? So if you divide 4,000 pounds by 27, 4,000 divided by 27, that's saying that the average person needs to weigh about 148 pounds. Okay, so we're saying, is it reasonable? Is it even possible that we could have 27 men on this elevator and the average weight is 148 or lower? And so the way the question is actually worded is, what is the probability that one randomly selected male has a weight greater than 48 pounds? And then find the probability that the sample of 27 adult males has a weight greater than 148. And so the first problem, part A, is really what we learned in the last section. So there's no central limit theorem needed here because we only are talking about one person. And so in this case, we're just looking, think about on a normal distribution, because weight of humans is normally distributed. So if we imagine everybody's weight in the United States, for example, that would be a normally distributed set of data. So we're looking at 148. The mean, it says that the mean for all adult men is 189. And we want to know what is the probability that we're going to be above 189. So we can figure out our z-score for 148, and that'll give us the percentage that we're below. And so that's going to be z equals 148 minus 189 divided by 39, which is negative 1.051. And we could look that up on the table, or we could also find this on the table. I think it turns out to be about 0.1466. We can take a look, actually. Let's see. So if we go to the table and we're looking for negative 1, I will probably only get negative 1.05 is as close as we're going to get on the table. And so negative 1.05, negative 1 is here, 0.05 is this column, and so negative 1.05 is giving me 0.1469. So that's using the table, we get 0.1469. So 1.1469 on the table, or using the graphing calculator, we should get a more accurate answer because we're able to put in more decimal places. And so to do that on the calculator, remember we go to second, distribute, and we're looking for the normal CDF, enter, and we're looking to go up to 148. So our upper is going to be 148, where our mean is 189, and our standard deviation is 39. So if we use the calculator, we get 0.1466. 0.1466 using the calculator. Okay, so that gave us what that gave us just now is the percentage that's going to be below this. So the probability of X of one person being greater than 148 is equal to 1 minus 0.1466, or if you were using the table, 0.1469, and that is 0.8434, which means about 84.3% of the men, or the probability of choosing one male that is greater than 148 pounds is about 84.3%. Okay, so that's, like I said, this is not applying the central limit theorem because we're only talking about one person. But in part B, this is where we're going to apply the central limit theorem, because we're saying, there's a decent chance that, but not, it's not like a guarantee that when we pick one person that they're going to be more than 148 pounds. But let's see what happens when we're picking an entire group of 27 people. Okay, so to find this probability, we're going to set it up the same way, but we need to calculate our sigma for the our standard deviation for the mean. And the standard deviation for the mean, the central limit theorem says, is sigma over root n. And so our standard deviation is 39, and our sample size is 27. Now, remember in the highlight up here, we said it has to be greater than 30 unless we know it's a normal distribution, and the male weights are normally distributed. So since male weights are normally distributed, we don't need to have more than 30. Sample size of 27 is just fine if we know it's from a normal distribution. Okay, if it was from a distribution that we weren't sure if it was normal or not, we would want to make sure we had more than 27 people in our sample. So this is approximately 7.50 if you type that into your calculator. Okay, so we're going to use that now. So what we're trying to figure out is similar drawing, 148, 189, but the difference is now we're using this as our sigma, and so if we use the calculator to get our percentage, the probability that the mean of our sample is greater than 148 is going to be 1 minus the z-score for 148, 189, 7.5056, and so using the calculator again, we'll go second, distribute, normal CDF, and this time our mean is our standard deviation. Our mean standard deviation should be 7.5056. And when we enter that, now we get a very, very small number. We want to do actually 1 minus that, and we get a really large number. That is 0.9999999. I think we need one more 9, and then 765 or something like that. Let's see, what was it? 1, 2, 3, 4, 5, 6, 7 9s, and then 765. So 1, 2, 3, 4, 5, 6, 7 9s, and then 765. So that is very, very, very close to 100%. So almost 100%, not quite, but very, very close to 100%. So that means when you have 27 men, there's almost a 100% guarantee that the 27 men that are on that elevator are going to exceed the 4,000 pounds, because if the average weight is more than 148, then they're going to go over the 4,000 pounds. So it's almost a guarantee that if you have 27 men, their combined weight will be more than 4,000 pounds, or in other words, their average weight is more than 148 pounds. Okay, so that's one example of using the central limit theorem. All right, so question number 2 is similar to the part B that we just did in the previous problem. So this time, this is saying the average drive to work for, let's say, all Americans is 9.6 miles. Or this might be data from a given state, but let's say everywhere in the United States, the average drive time driving to work is 9.6 miles. Or not drive time, but drive distance is 9.6 miles. The standard deviation is 1.8 miles. Okay, so we know our mean is 9.6. We know our sigma is 1.8. If a random sample of 36 employed people who drive to work are selected, find the probability that the mean of the sample will be between 9 and 10 miles. And so we know our mean is 9.6, and so between 9 and 10 miles, we're trying to figure out what is this likelihood that that the mean of those 36 people we pick is going to be in between 9 and 10. Okay, so we want to calculate the standard deviation of our sample means, and that is the normal standard deviation, which is 1.8, divided by square root of 36. So that is 1.8 over 6, or 0.3. Okay, so now we can find the probability that our sample mean is in between 9 and 10 is, so what we can do is we can do our normal distribution of 10. So we'll go 10 with our mean of 9.6 and a standard deviation of 0.3 minus the normal CDF of 9 minus 9.6.3 and 9 and 9.6 and 0.3. So basically what that would be doing is it would be finding all of this area and then subtracting this area, and what we'd be left with is the area that we're looking for right here. Or on the calculator, you can actually say you want it to go from 9 to 10, and so you could do that here by going to second distribute, normal CDF, and for our lower, we can just say 9. For our upper, we can say 10, and then the mean is 9.6, and the standard deviation is 0.3. And so that comes out to be 88.6% or 0.8860, and that is 88.6%. So that means there's an 88.6% chance that our sample of 36 employed people is going to be between 9 and 10 miles. And that's it for today's lesson. You guys all have a great day.